Hey everybody, we're going to learn about 6B today. It says, I can plan and carry out investigations to determine how temperature, surface area, and agitation affect the rate at which a solute dissolves in a specific solvent. So we're continuing to talk about solutions at this point. I do want to take a second and just remind you about how we create a solution. So we do take a solute and put it into a solvent. Then we have to do some kind of agitation, heating, stirring, increased temperature, something like that in order to get it fully dissolved, okay? And this is what this AKS is talking about. It's talking about the actual dissolving of the solute inside the solvent. So let's look at your AKS portfolio, and it should look something like this. It says the following model shows the process of dissolving sodium chloride NaCl, which remember is just table salt, okay? Using the model above, explain how each of the following factors affect the rate at which something dissolves. Alongside your explanation, propose a simple investigation that could be performed to confirm your proposed explanation. Be sure to identify how the investigator will know that each factor had an impact on the rate of dissolution. That just means how it's dissolving. Okay, so if we're looking at our substance, these are water molecules, okay, and then we have our salt molecules, the Na and the Cl. Notice it's showing you the charge, Na positive, Cl negative. And then it's showing you what's happening once it's dissolving. And you can see the Na is separating from the Cl within those water molecules, all right? So they will not stay together because this is an ionic solution, okay? So what you're going to do over here is you're going to write your proposed explanation and your proposed investigation, or what kind of science experiment can you do to actually see this happening, all right? We're going to talk about each one of these separately. So here's some methods for dissolving solutes faster within a solvent. If you were to look at this one, the first method is heating, okay? They just added a flame as heat. They have some sugar in water. They put it in. The sugar is just sitting at the bottom. All right. It has to have something happen to it for it actually all to dissolve. Otherwise, it's just going to sit there. So one way of doing that is to heat up the water. If you heat up the water enough, that is going to end up dissolving the sugar much, much faster than if it was just sitting there. Okay. Now the same goes in reverse though. If you were to cool down the water, sugar will not dissolve as much sugar will not dissolve at a lower temperature, okay? So you'll have more sitting at the bottom, and we'll talk more about what that means next week in our next AKS. So if you look over here, this one is saying, hey, just stir it, classic, right? So you have some water and some salt at the bottom that you just poured in, and it's just hanging out. We need to actually dissolve it and create a solution. Easiest way to do it is to stir it up. So if you stir it, it will end up dissolving, but let's say you added too much salt, like you just kept pouring it, you added too much salt, you're stirring it, and it's still, like most of it's dissolved, but there's still a little bit there at the bottom. How else can you dissolve the rest of that salt since you've already tried stirring it? Well, heat it up. Take whatever is left in your solution, put it over top of a flame or some kind of heat source, right? And it will increase the temperature of the water. All of a sudden, more of that solute will be able to dissolve now at higher temperature. And then another method is to reduce the surface area of your solute. A really good example of this is coffee. All right, coffee beans, you can see this is a whole coffee bean right here. They're over here as well. They're, they're pretty big, like that size. Well, if you're making coffee, you don't want to use a whole coffee bean in order for the hot water to percolate. Yes, we have increased temperature, right? But it's still going to be some pretty weak coffee. If you want stronger coffee, what you do is you take the coffee bean and you grind it or you crush it, right? So that you can create small little small pieces which have a lot more surface area on the outside for the water to actually touch, okay? So before, the water could only touch this outer bean, Now all of a sudden the water can touch all these teeny, teeny, tiny little coffee grounds, and we can have a much stronger and highly concentrated solution compared to what it was before with a diluted solution with a whole coffee bean. Okay, let me show you something else. Okay, so this is just a simple simulation I wanted to show you. Here we have a container filled with water and we have some salt. So if I shake the salt in here, what you can see happening is that my salt concentration is growing. So it was flat because I had no salt in there originally, and then the concentration has grown over time. Once I start shaking, more solute into a solvent equals a higher concentration. If I go ahead and I add more solvent, in this case my solvent is water, what do you think is going to happen to my concentration level? If you said go down, you are correct. So if I add some more solvent, you can see I am reducing the concentration of my salt, okay, NaCl. Now, I'm going to go ahead and I'm going to test the conductivity. So you can see here I have a light bulb, it's connected to a battery, and then we have these little probes. If I pull this out and I put it inside this solution of salt water, my light bulb will shine, okay? And that is because it's ionic, right? NaCl, Na is a metal, Cl is a non-metal, so it's an ionic solution. Now I want to show you what that looks like on a molecular level. So if I shake, remember sodium chloride is just salt, we're still looking at salt. So I'm going to shake my salt in. Notice what this is looking like. They started out in big chunks of Na and Cl. You can see my Na is purple, my Cl is green, but they don't stay together, okay? They drop down in the molecular form. Now they spread out as atoms, okay? These ionic bonds. So it will dissolve and spread out within our water molecules. Now I'm going to switch back over here and I'm going to remove the salt from our water, and I'm going to go and I'm going to show you sugar. But first I'm going to dump out some of this water just so we can kind of be back at starting point. All right, so I'm just going to shake some sugar in here. If you guys remember anything about sugar, sugar is a covalent bond. It's made up of all nonmetals. So notice what's happening. I'm shaking my sugar and my graph is going up on the concentration of sugar. I dumped it all in there. So it was at 0. My concentration has increased, okay? If I check the conductivity of sugar, what do you think it's going to be? If you said that it's not going to conduct electricity, you are correct, because sugar is made up of all nonmetals, so it will not be conducting any electricity. And then if I go ahead and I add some water, which is solvent, to my solution, you're going to see that my bar graph is going to go down and reduce that concentration. So it's going to become more and more diluted as we add that extra solvent. On a molecular level, let's go ahead and reset this. We're going to do sucrose, which is just sugar. Okay, so now we're going to shake it in, and you can see what that looks like. It forms molecules, right? The molecules dump down into the water, and notice what's happening here. Those molecules are staying together. They are not separating out into atoms like salt did, because salt is ionic. So when covalent ends up dissolving in a solvent, they will stay in their molecular form. They will not separate out into atoms, okay? That pretty much covers 6B. Thanks, guys.